We are now on page 8 of the AP Chapter 4 packet, and we're going to be looking at an example of how to do a calculation for a redox titration. I took the liberty of drawing this all before the video just so I'd have it all written out. If you want to pause and copy this down, great. This is a burette, and it has the permanganate ion in it, even though this says that it's, well, it doesn't say it's a potassium permanganate solution, but if it did, you would only care about the permanganate. They give you a molarity and a volume of this, and the way they got the volume of this is they read the volume in the beginning, and then they read the volume at the end, and the difference is going to be the volume that they wrote there. So they're titrating a hydrogen peroxide solution with permanganate, and they're dropping the permanganate in to the hydrogen peroxide until the titration is over, as indicated by a color change. And this is the volume of the hydrogen peroxide that was given in the problem. So 10 milliliters of this required 15.2 milliliters of that, and we know the molarity of this, and we're going to get the molarity of that. So this is going to lend itself to the traditional problems we've been doing, where molarity equals moles over liters. The only problem is we don't know the ratio in which these two react, which is going to play a role in how we get the balancing of a redox. So it tells you that this is an acidic solution, so we're going to incorporate balancing a redox in acidic solution as we learned before. So we're going to write the MnO4 minus, I'm going to be using the shortcut method because that's going to be a lot quicker, and the hydrogen peroxide. And they're telling you that the products are going to be Mn plus 2 and O2. So we'll write Mn plus 2 and O2. What we're going to need is the oxidation number for each element. So we'll quickly put that in. Remember in peroxide that the oxygen is -1. So -1 for the oxygen there. That's a +2 and that's a 0. So if we look at our element electron step, we're going to go down with the Mn by 5. We're going to go up with the oxygen by 1. The least common multiple of 1 and 5 is 5, so we're going to want 5 oxygens on the left for every 1 manganese on the left, and the same on the right, of course. And this is where we're going to run into that problem of even and odd numbers. If I want to have 5 oxygens on the left side, this 2 is going to throw me off. I'd have to put a decimal like 2.5, and that's going to be a real disaster. You definitely don't want to do that. And this 5 does not have to be the coefficient. It just means the total number. So if you put a 5 here, you actually have 10 oxygens. So what you're going to need to do is double this to 10 and 2. Again, these numbers are the total numbers of that element that you want on both sides. So if you want 10 oxygen on the left, you put a 5 here. And of course, you would also need a 5 here. Then if you want 2 Mns on the left, you put a 2 there, and you put a 2 here. And that's good. Now, I could continue this redox and balance it completely, which I will. But for this problem, you wouldn't even have to do that because all you care about is this ratio of 5 to 2. But just because we've practiced before, let's finish balancing. I've already used these O's to balance those O's. So when I do my water step, I'm only going to care about these O's. They're going to be 8 waters on the right that I'm going to need to make 8 oxygens. So 8 of these O's I need because this already balanced with that. Then I need to do my H's. I have 16 on the right, but be careful because you already have 10 on the left. So therefore, you would only need 6 more H pluses, and then you would be done because you're not in a basic, you're in an acidic, and so you're done. But again, you only really need this 5 to 2 ratio. So what I'm going to do is I'm simply going to solve for my moles of the permanganate. So I'm going to take 0.103. I'm going to multiply that by 0.0152, and I get 0.00157 moles. That's rounding with sig figs because 3 sig figs is good. And now what I need to do is understand that that is the moles of permanganate. So 0.00157 moles. I need to know how many moles of peroxide that would need, and I'm going to need to use the bridge for that. So I'm going to take this 0.00157 divided by 2 times 5, following the bridge. Divided by 2 times 5. Of course, you could do proportions if you prefer. Times 5. And that's going to equal 0.00393. 0.00393 moles. So the bridge, don't forget, was divide this by 2 times 5, and you would get that. So there are my moles of the hydrogen peroxide. All I need to do is copy that over here, 0.00393, and then divide that by 0.01, and we find out that the molarity is 0.393. This problem is really not any different than all the other stoichiometry problems with solutions. The only difference is you had to balance a redox to do it. Once you balance the redox, you do molarity equals moles over liters, solve for moles, bridge from this moles to that moles using the stoichiometry of the balanced equation, then get your answer, put it here, and find the missing concentration. So now you're ready to do the next page as a practice.